Morning. How you doing? You're here on Sunday. What are you doing here? Okay, let me open this one. Is that the yes? Okay. Okay, so I already have a few questions. First, you guys know how the opioid, all of them, um, except with the ones that has OH group at the position 14. Anyway, all of them causes antitussive activity. They could be used for cough, right? Which isomer suppresses the cough, the dextro or the levo? Okay, both. The right answer is both. Why is that? It has to do with the, it has to, it, well, I mean, that's the next question. But before that, why is it that both work? It has to do with the receptor itself. We don't know what the cough receptor actually. Some hypotheses say it's the NMA, something like that. But whatever that receptor is, for that cough receptor, isomerism does not matter. Okay. In fact, I have a nice analogy I want to share with you since you asked the question. So, say again. Page 14. Sure. Okay, sure. Page 14. One of the discussions, I think it's stop reading at page 14. Okay, just remind me after I explain this, okay? Okay. Thank you. Sorry. No, you're fine. All right, I'm horrible at drawing this, apparently. No, I'm not doing a good job. So think of this as a 3D glove. And here, this is a 2D glove. Okay. So this would be the mu opioid receptor. And this is the cough receptor. Well, first of all, does it make sense? This is a 2D and 3D glove. So, well, let's start by the idea first. So when you have a like a 2D shape of a hand, it can fit the right hand or the left hand, because it does not matter. You could, fit this way or that way. This is my right hand. This is my left hand, right? I can fit it both ways, because for that receptor, it only cares about the 2-dimension of the hand. So both hands can fit. The cough receptor is of this kind. It does not care which isomer, the D or L, they both can fit the cough receptor. Okay? But the opioid receptor is like a glove. The right hand has to go with the right hand glove. The left hand has to go with the left hand glove. And in the case of the opioid, which one is the one that binds to the opioid? Is it the dextro or the levo? The levo. So the levo is the form that binds to the opioid receptor. So think of the opioid receptor as a glove, left hand side of the glove, and only the left hand can bind to it. Okay? The cough receptor is like a 2D shape, so I could use my right hand or I could use my left hand the other way, you know, it's not gonna matter. As long as you have 5 fingers around, you know, arranged this way, it can bind and give you the anti-cough activity. So both dextro and levo can fit. So dextro or levo work. In this case, only levo work.
Okay, something easy to make it memorable. If someone has a call and they're patient, you don't forget to put on your disposable gloves that fit both hands.
Sure. Yeah. So if somebody has a cough, and you should what? Put your
The little latex gloves.
Yeah. Yeah. The little.
So
Yeah. Sure.
maybe
Yeah.
it'll help.
Yeah. Help me memorize it. Yeah. Okay. So the latex glove can actually fit both hands. But as far as the receptor here, it fits both hands, right? Now for the opioid, it only requires that, you know, the left isomer, the levo isomer to work. Does that make sense, guys? Yeah, it does. Okay, so now, since you know that both dextro and levo work in case of the cough, if you want to design a drug to help with the cough, which one would you choose to prevent people from abusing it? Dextro, right? Why is that? Why? Because it will give you the anti-cough, and it's not going to bind to the opioid, so you prevent abuse, right? Which is the reason why we have, what is it called? Dextromethorphan, right? Over the counter.
And if we forget that the levo binds the opioid, we can like think about this, go, oh, we have dextromethorphan, that must be the other one, the levo.
Exactly. That's why we have the dextromethorphan over the counter, and because we know that the dextro is not going to bind to the opioid receptor. So how do people then abuse it? Why do they take higher dose and can, you know, robotripping? You've heard of that, of the term robotripping? People who use the dextromethorphan to get high. They force it. Yeah, they force it. It's like imagine you have the left hand glove, and then you try to force your right hand into the left hand glove. Okay, I mean, it's not going to have the best fit, but if you try to force it at higher concentrations, it can still bind. Okay, make sense? Okay, so that's a good question. And you also had a question about the exercise of the central analgesics. You want to go through the exercises. We can do that. Was that your question about the cough and opioid, Morgan? Was that your question, or do you have a different one? That was yours. Okay. Oh, I know, you had asked about the autoreceptor. Okay, so we have a question about the autoreceptor. John, did you have a question? I know I stopped you in the middle. I just wanted to explain that. Okay, so let me, yes. Yes, yes, yes. Okay, so remember when we had different ways of enhancing the affinity? Apparently, somehow, if we add an OH group at position 14, I really want to make sure this is the right information because sometimes I forget. Does anybody remember that? That all of them has antitussive except those who have certain function group. Do you guys remember that? Position 3. R3. Okay.
Dexter Levo. It isn't in the notes, right?
About the cough suppression.
Mm-hmm.
It is actually, it is here. I'll show you. I'll show you what it is. It's here. Talks about stereochemistry, Dexter and Levo. Okay, it's in page 6. So, in case you're wondering where this in the notes, it's in page number 6. Okay, it talks about the Dextro and Levo and why do we have Robitussin over the counter, because it's Dextro and we think it's safe, you know, but some people abuse it, but the concept applies. Okay, it's actually at R3 here. Okay, so which is, I think, numbered as 14. Okay, so I was right. You're wrong. You said R1, right? You said R3? Okay, so we're both right. Okay. Okay, so it's, see how R3 here, which is carbon number 14. Okay, at this position, remember when we added the OH group here, we enhanced the potency of these opioids. We had like a table with 6 different molecules, and some of them had OH group here. Those who have OH group here, for some reason, they lose their antitussive activity. It actually decreases their antitussive activity, okay? So they become more potent when it comes to binding to opioid receptor, and they have great potency, and yet the antitussive activity is lost for some reason, or it decreased, to be more accurate. Yes? Excellent. Yes, which one of these help you decide if the drug is an agonist or antagonist? R1, which is, again, I hate for you to, memorize R1, 2, 3. Just remember the nitrogen here, okay? Just in case if it's numbered differently, okay? So you don't get tricked, because we like to trick you sometimes, right? We put R5 here instead of 1. So if I number them 1, 2, 3, 4. Anyway, so nitrogen, any substitution of nitrogen is the one that decides whether it's agonist or antagonist. So what would you have as an agonist on the nitrogen? Methyl group, right? The antagonist will have the methyl cyclopropyl, right? It's this rectangle, triangle with methyl, and there's another one which is ethylene, right? Methyl ethylene, double bond. Okay. Yes.
R1 set up like an antagonist
Mhm.
on something that would otherwise be an antitussive. It would inactivate antitussive activity as well.
Oh, that's a good one. I'm not sure. I'm really not sure. Yeah. Yeah, I don't know. Yeah, I mean, because it's studies, experiments are the ones that decide. I know she was asking earlier. Yes, ma'am. Go ahead. Excellent. So guys, remember, what's the pharmacophore for this molecule? For all the opioids? Which part is the pharmacophore? Because this will answer your question. It's this part here, the phenyl and the nitrogen and this part. So this part carries the what? The message or the address is responsible for the message. Basically, you have a message, you go to the address and tell them, I'm going to be an agonist or antagonist, okay? Because of the nitrogen here, okay? The remaining of the part will help you select the different receptors. So it will be the address, okay? Does this answer your question? Okay, so this part is the message. So a modification on the nitrogen will make the message either, will make the message to the receptor to be, agonized or antagonized. The remaining part will decide which receptor you should bind to. Is it a mu, delta, kappa, whatever that is. Okay. Melody? Yes. Yeah. Anytime you see an epoxide, that's a sign of toxicity. Yeah, but there's no epoxide here. Do you see an epoxide?
No, I just maybe.
Okay, sure. John?
She was asking the effects of R2 as far as, I know it's part of that.
What does it say in the note about R2? I'm sorry, guys, I can't hear. Hi. Yes. Okay. So that does not contradict with the binding to the address itself. So for this part, to be active, it has to be OH group. Okay. If you block it and add CH3 here, it becomes a prodrug. It becomes inactive. Okay. We're still talking about the same receptors, mu or kappa, but it applies to both receptors. Now, if you wanna selectively make the drug bind to mu or kappa, then you're gonna play with this part here, okay? So modifications to this part will help you decide if whether you should bind to mu, delta, or kappa. But then this part helps you whether the drug will lose activity or not. Like if you add a CH3, then activity is lost. If you put here methyl or cyclopropyl, whatever that is, it becomes an antagonist, okay? In fact, if you keep extending the size, on this part, it moves, from agonist to partial agonist to antagonist back to agonist. But we're not worried about that, okay? It's just for experimental. That's what they found out, okay? Anyway, did I answer the question, Millie? I did. Somebody else has a question about this? Any questions, guys? Okay. Should we talk about the autoreceptor? What is this part called here? Presynaptic. And this is post. Okay. No, we're talking about the autoreceptors, which applies everything, okay? Dopamine, norepinephrine, anything, okay? So I guess in order, I think the best, scenario to understand what autoreceptor do is imagine, neurotransmitter being synthesized, stored in these vessels, and then released, okay? So, and then there's a receptor here, which is postsynaptic. They bind to that, produce the signal, and that will happen normally. Now imagine if you have more of this neurotransmitters, right? So they're gonna flood. Some of them are gonna go out of the synaptic, and guess what? They're gonna bind here, right? So when they bind here, it's a sign to the presynaptic neuron that we have too much neuroreceptors. Please stop synthesizing these neuroreceptors. Negative feedback, okay? So this is a receptor here. It's called autoreceptor. Stimulating this receptor, basically acting as an agonist, would lead to inhibition of the release of more neurotransmitters. Okay, so this is a way of basically, preventing the release of neurotransmitter. Does that make sense now? Okay. On the other hand, if you design an antagonist, it's going to do the opposite, right? So antagonist here will block the autoreceptor, which means no negative feedback, which means more of the release, okay? Are you talking about the autoreceptor? So the neurotransmitter, when the neurotransmitter release, it works on the post. Yeah. So exactly. So if you antagonize the autoreceptor, you stop the inhibition and you get more of the neurotransmitter. Questions about this, guys? Any questions over there? Say it again. Reuptake, okay. Now, another way to think of this, another pathway to consider is, let's see, running out of colors here. Yeah, I'm very visual when it comes to education. It's okay. It's okay. Thank you. So there's another one here called transport protein. Okay, this is a transporter. So when these again are released in extra amounts, they are reuptaken back and stored and used again to be released. So this is what normally happens, too much of these neurotransmitters, then they go back to the reuptake, to the protein transporter that reuptake these neurotransmitters back into the neuron, presynaptically, and storage them in vessels and then release them again, okay? So some drugs act by blocking this reuptake, okay? And guess what? What happens when you block this? More neurotransmitters will stay here in the synaptic area, and they bind, so they produce more of the agonist effect. Can you give me an example of drugs that work by inhibiting reuptake? SSRI, right? Serotonin selective reuptake inhibitors. That's what SSRI stands for. they selectively inhibit the reuptake of the serotonin. Other drugs are the norepinephrine, the selective norepinephrine reuptake inhibitors, the SNRI. Okay. I think it's the SN and not the
They
NSRI.
have an SS, I think, Cymbalta and maybe a mix, I'm not sure. I don't remember, I shouldn't mention effects since I can't. But I think it is a SSRI
And yes, of course, yeah. Some drugs inhibit both norepinephrine and serotonin. So it's SNRI. Okay. Yes.
Okay. Since we obviously now know that there's a norepinephrine reuptake inhibitor and there's a serotonin reuptake inhibitor. One, do we have to know that specifically for those type receptors and the other, and which molecules are taken up by reuptake inhibitors that we've covered, and which ones have autoreceptors? Since autoreceptors is going to be in each separate day's worth of reading, it's wondering, will we have to know serotonin has an autoreceptor, norepinephrine has a reuptake receptor? I don't know if it has an autoreceptor.
Okay. So
if that's something we have to know, do you mind giving us a list? Like which ones have autoreceptors, which ones have reuptake?
Okay, well, I think all neurotransmitters have autoreceptors. All of them have reuptake inhibitors. That's a general mechanism that for all neurotransmitters, that's how they are controlled. You know, I can't think of any exceptions, but most neurotransmitters have. Yeah.
Until you said that, I wasn't.
Sure. Okay. As far as I know, it's not, there's no exceptions, but if there is any, then, for the purpose of this course, just, trying to know the focus, the general concept of how these work. Now, structure-wise, tricyclic antidepressants work as what? What's the mechanism of action for anticholinergic? But how do they inhibit? Well, they have the side effect of anticholinergic, but how do they release the norepinephrine and serotonin? What's their mechanism of action? Tricyclic antidepressant. They actually, let me double check, because I think I want to make sure before I say it. Okay, let me get back with that. Do you remember the mechanism of action for the? Okay, you have a question. Yes. Yes. Sure. Yeah, that's a good way to think about it. But so experimentally, this has been a successful way to increase the effect of the neurotransmitter. I mean, that's a good way to think about it. But any other questions, guys? Yes. So I believe they block the uptake of both norepinephrine and serotonin. But I wanted to talk about the fact that there is tricyclic means 3 cycles. And then when we broke the one in the middle and we left only with 2 cycles, then it was more selective to the serotonin. Okay. So structure-wise, it's the middle ring when broken makes the drug more selective to the serotonin rather than, you know, inhibiting reuptake of both. Any questions? All right, so autoreceptor is understood. So, all right, what about, speaking of auto induction, everybody is clear? Because I keep receiving emails about the auto induction. Yes, so this is a totally different story. It has nothing to do with the autoreceptor, okay? So auto induction is just like two drugs interact with each other. One induces the enzyme that metabolizes the second one. In the auto induction, the same drug induces the enzyme that metabolizes itself. Okay, an example of this is carbamazepine, that's true. What else? Phenytoin, okay? That's why it's hard to control their you know, level in the blood, because yes, you must be monitored, and they have a okay. Questions, guys? Okay. Do you have a printed out notes? Because I forgot to bring my antidepressants. Good, thank you. The antidepressants. Oh, I got it. Thank you, guys. Yes. Thank you. Okay, so first of all, for your information, you didn't have to memorize this SAR. It will be given to you, okay? You just have to use it. You know how to use it, okay? Yes, sir. Sure.
So are dopamine and acetylcholine true inverse of each other? Like I know their amounts are like on a scale. Their amounts, like if you have too much acetylcholine, that means you have too little dopamine and vice versa. Does that also affect its effects? Like if there's too much acetylcholine, then that means that you have Parkinson's. If there's too little, you have acetylcholine.
Yes, just like the CISO. Is that what you call it, CISO? Yeah, CISO. So yeah, so acetylcholine is sitting on one end, and the dopamine is sitting on the other end. If you have more dopamine, okay, means you lost the effect of the acetylcholine, and you get more psychosis, hallucinations. Yes, and if you have more acetylcholine, then you end up with Parkinson-like. Okay, so you have no dopamine. Okay. So for the SAR, guys, so again, it will be given to you. So in this case, if we add you know, a fluorine at position number 7, which is electron withdrawing group, what happens to the activity? Increases. At this position here, at the nitrogen, if we replace the nitrogen by anything else, okay? If we replace the nitrogen by oxygen, by carbon, sulfur, anything, what happens to the activity? It's reduced or lost. So the optimal activity is when you have a nitrogen, okay? What else? The carbonyl, the carbonyl group here is important for activity. 1,2 fused ring is also important for activity. So you need the hydrogen accepting group, which is a carbonyl. Right, this part here, let's finish this one here. So at the phenyl group, anything at position 2 or 6, which is here, ortho, would increase the activity, okay? Anything at position 4 would decrease the activity a lot, so 2 arrows, okay? Okay, this part here, at position 3, so this drug, I mean, the way it is without an OH group, if a drug is given like that without an OH group at position 3, then when it goes to the liver, it will be metabolized by adding an OH group at position 3, okay? This metabolite is an active metabolite, okay? Normally, when you metabolize a drug, it becomes inactive, but in this case, the metabolite that has an OH group is active, okay? So then the drug will circulate again, produce more effect, and then go back to the liver, and then be metabolized the second time, which is phase 2 metabolism, and a glucuronic acid, this long chain of OH groups, when we talked about the example of the hangers. So now we have the 6 hangers together that will bind or be attached to that OH group in position 3, and now the drug become inactive. Okay, so in this case, the drug has a chance to produce activity by itself, and then second time as a metabolite with the OH group. And then finally, when it's metabolized in phase 2, it becomes inactive and, get excreted. So this will increase the duration of action, okay, for the drug. So basically, having no OH at position 3 will buy us time to increase the duration of action, because the liver had to add an OH group, the drug's still active, and then it's metabolized at the second stage. Now, if you have a drug that already has an OH group at position 3, okay, so we have saved the liver the work to add an OH group. So guess what? The drug will be, producing the activity, and then when it reaches to the liver does not have to add an OH group. It's already there. So it uses the OH group that's already been there to add the glucuronic acid and make it inactive. And then the duration of action would be shorter. Okay? If you like to memorize things better than going through all this, just think of having no OH group means longer duration of action. Having an OH group means shorter duration of action. Okay, so you could choose either way. But yeah, the whole figure with the words. Okay, but the concept itself applies. Not only this, it could be at any drug. In fact, one way of increasing duration of action is by designing a drug such that when it's metabolized, it is still active. Okay? Get that, everyone? So it does not have to be this example, okay? Anytime you have a drug that is metabolized and the metabolite is still active, what happens to the duration of action? Longer. This is one of the techniques of increasing duration of action. Can you tell me another technique of increasing duration of action? Make it more lipophilic. Okay, but there's an exception to this rule. Huh? Benzodiazepines and barbiturates, which are the ones that work centrally at the CNS. They cross the blood-brain barrier. Why are these an exceptions? Yes, so because when they are more lipophilic, yes, they cross the blood-brain barrier faster, but they also leave faster because they go redistribute to the fatty tissues outside the brain. Okay, so this is an exception. And this applies to all the CNS drugs. When you make them more lipophilic, yes, you increase the ability to cross the blood-brain barrier, but then they will have a shorter duration of action because they leave outside the brain to the fatty tissues. Like which drug? We have two examples so far, the benzodiazepines and barbiturates, okay? But generally, the concept applies to all the CNS, okay?
Are you remembering from the lecture?
So if you see two structures, will you be able to know which one is more lipophilic? Yes? You should know, right? So if you see two drugs, then you should be able to tell which one is more lipophilic than the other, right? You just compare them, see which one has more, carbons, right? You don't have to do the whole empirical method to calculate how much, but you could compare two drugs and see which one is more lipophilic. So if one is more lipophilic, what happens to the onset of action first? The onset, it's going to be faster. What happens to the duration? In case of the, centrally acting, shorter, okay? Yes, I know you had a question there, I'm sorry. Yes, John.
I'm assuming, just because Promise was asking this when she reminded me, what drug do you add in I guess it's in a CNS agent you talked about, and the peripheral enzymes break it down, but the drug you add to inhibit that doesn't cross the blood-brain barrier, so you get more effect in the CNS because peripherally.
Oh, levodopa. You were talking about levodopa? No?
Okay.
Okay.
So you add levodopa to
Carbidopa. So yeah, that's another mechanism. So that's another thing. So I hope. Okay. Your question? Diazepine? Excellent question. So what happens, guys, to those that go out and bind to the fatty tissue? Have you heard the residual effect? What's a residual effect? It means you still have some of the effect of the drug after you stop the drug, but you have like minor effects. So these benzodiazepines, they have the residual effect, which means you stop the drug, okay? But those molecules that went to the fatty tissues, now when the drug is stopped, the plasma is, the blood is free, they leave the fatty tissues back to the blood and they can cross the blood-brain barrier and cause some effect. But depending on how much effect you have is how much dose you have taken. So you have minor effects, and that's why people stay drowsy, and even though they start the medication, but they still feel drowsy. So that's why benzodiazepines, if you try to treat, give them to help, sleep, you want to make sure you select the short-acting ones, but then they still have the residual effects for the rest of the day. The other kinds, the non-benzodiazepines, okay, they are very nice. They just bind and leave, and boom, you're awake in the morning. You don't have to worry about any residual effects, okay? Somebody else was raising their hand for a question. Yes, yes, I'll come back to you. Yes, go ahead.
Back to opioids, what was the benefit of using partial agonists?
Okay, guys, what's the benefit of using a partial agonist over the full? First, you don't have this, it eases it, well, so it's easier to wean somebody off when you give a partial agonist, right? It has less respiratory depression because it's partial. It does not fully block the respiratory center. It can, less conservation, but also it also has less potential for abuse, right? Okay. And you can think of the partial agonist as partial antagonist as well. So if somebody, has been, let's say they took overdose of an opioid drug, the ideal treatment is to give antagonist. But if you don't have antagonist, let's just pretend, then can you use the partial? You can, because partial will substitute, will compete with the receptor, with the agonist, and then, produce less effect. Maria, you still have the question? GABA binding site? Okay, before we switch topics, you have a question? Okay, so if somebody has overdosed an opioid and used the antagonist, would you have a withdrawal effect? What do you guys think? Yes, you will. In fact, if you use the full agonist and you give a partial agonist, you have withdrawal effects. So if you give antagonist, you even get worse withdrawal effects. But guess what? Which is more important, withdrawal effect or saving somebody's life? Right? Say it again. Exactly. So the first step to save their life is to give them antagonist, bring them, back to life, breathe, so they get respiratory system is working, and then of course you wanna give them partial agonist to wean them off for some time, and then gradually decrease. Okay. Yes.
So would that be the same for the K agonist / partial?
True. Actually, in the notes, whenever it says kappa agonist, partial mu antagonist, it should say partial mu. It should say mu partial antagonist. Okay. Yes. The only thing with the kappa, they're not using them anymore, is it causes anxiety. Okay. Dysphoria. So it's the opposite to euphoria. So it makes people upset. In fact, in one long time ago, someone was asking me, why don't we give, last year class, they were asking me, why don't we give the mu agonist combined with the kappa agonist? This way you cancel the euphoria by dysphoria, you get them to neutral, and then you get the analgesic effect. In theory, it looks great, but then apparently the dysphoria and euphoria, they don't cancel each other. It's like, you get the euphoria, but then later on you get the dysphoria. Think of an example of hangover, right? So you get the euphoria initially, but then the next day you get like these dysphoria and anxiety. Not the best example, but anyway. So it does not mean that you give these two that they cancel each other, okay? Yes, ma'am. Multifunction, okay, multifunction signaling. Okay, this is a different topic. I know Maria also has a different topic, so I have two new topics. Anything here before we switch topics? Okay, so that's the third one. The caffeine effect and smoking. Okay, so guys, this is a short answer. So caffeine is just like a drug, and cigarette smoking, tobacco is just like another drug. So the caffeine is an inhibitor to SIB something, one of the enzymes. Smoking is an inducer to one of these enzymes. So think of them as drugs. So if you want to think about the effect of smoking or drinking caffeine on another drug, just think of the caffeine or smoking as one drug affecting another, okay? And then just treat it like the case of the drug-drug interactions, okay? So the smoking would induce metabolism, so you'll have lower dose, have underdose, okay? Caffeine would inhibit the enzyme, and they would have overdose, okay? If you drink caffeine and smoke at the same time, depending which one is more, then you balance them. Just for fun. I'm not sure if which one is stronger. What about Parkinson effect? Okay, so generally think of whatever that drug is going to be affected, overdose, underdose, how this is going to cause more dopamine or less dopamine. Okay, so if it's less dopamine, you get what? More acetylcholine, which is Parkinson. Okay, so EPS, Parkinson or extrapyramidal symptom. You have a question over there? Of course, yes, yeah. You don't have to memorize what's the name of the enzyme. I will, give you. Just make sure you know how to use the information. Okay. Yes.
Tobacco and cigarettes, it has MAO, which means it isn't broken down, which means there's more dopamine. It's a culture to have that hallucination, psychotic effects. Okay, right. And so if the tobacco has MAO, that increase the amount of dopamine.
Right. So, okay. So the question was, how the tobacco affects Parkinson. So, experimentally, they have shown that people who smoke tobacco are less likely to get Parkinson. The hypothesis was because tobacco inhibits the MAO. Okay, but this has not been proved. So it's like you have you have some studies that shows the effect, but we're not sure what's the mechanism. No, caffeine, we're talking about caffeine, and it only inhibits the enzyme that's responsible for metabolizing, what is it? Clozapine.
Okay.
Okay.
So Parkinson's, caffeine, smoking, good. Psychotics, caffeine, extrapyramidal, smoking,
Underdose.
the underdose.
Yeah.
Oh. Okay, so
But
not
then
good,
but
just
if you
not
put them all
good.
together, you're gonna confuse yourself. Like break them down into
Yeah, I'm just trying to make sure.
smaller pieces.
I was sitting here going, well, I remember actually writing down
Okay.
extrapyramidal and I didn't remember writing underdose, but I knew I read something and it probably wasn't good. So I was just trying to make sure psychotics and the other, both of them seem to not work. I mean,
Okay.
both of them seem to help.
Okay. Okay.
But
Now
that's not a drug thing. That's they just generally help do caffeine and smoking help, even if you aren't getting drugs, or is it just an effect on the drug?
so the immediate effect of caffeine and smoking is on an enzyme that metabolizes clozapine. Okay, so this is the immediate effect, induction or inhibition. Parkinson is another story. It's some results, some studies shows that people who smoke are less likely to develop Parkinson, but we're not sure why. Okay.
So it's independent of the drugs.
Yes.
It's physiologically.
Somehow we're not sure. Yeah.
Or it's theoretically.
Yep. Okay. Now I forgot what were the other topics I wanted to switch to. Okay. I know Maria had one question about something, and you had the GABA. Okay. What was your question again? I'm sorry. Binding sites for GABA. Okay, so this is anticonvulsants. Somebody else had another question. What was your question? You're fine. Oh, multifunctional signal. Okay. Okay, so this is a quick one. Let me start with it. So the multifunctional, basically the same receptor at different regions of the brain. One time it acts as an agonist, another time it acts as an antagonist. One time it acts as an inverse agonist, another time it acts as a partial. It's the same exact receptor, but because it's located in different parts of the brain. Okay, so it's one receptor that has multifunctional. Okay, normally we have different receptors, so we can select one from another and select a function. Here, the problem is it's the same receptor, and when you design a drug for the receptor, how can you tell what's the function underneath it? Because if I'm the receptor and I'm bound in the membrane, I'm outside, this is my inside. So from outside, it's the same. It binds to the drug. From inside, I'm doing different functions, right? So how do I tell? It's challenging. No, MOA inhibitor is just an MOA is just an enzyme. Okay, so it's easy to inhibit, and then you get something else. Okay, you know, depending on whether it's an A or B. But as far as the receptor, it's the D2 receptor is the best example of this multifunctional. Okay.
And its effect is not based on, say, postsynaptic, presynaptic, postsynaptic, or inhibitory neuron, stimulatory neuron. It is actually the other side of the lumen of or the other side of the plasma membrane of the neuron. Whatever that receptor does becomes either a G protein or a channel.
Yes.
Or,
Yeah.
totally
It's a GPCR receptor. So it's from inside the membrane, it kicks in G protein, which could be inhibitory, stimulatory, whatever that is, different function.
Oh, okay, so they're all G proteins.
Yes, all of them are
They just have
GPCRs.
different effects.
Yes.
And it's not the inhibitory or stimulatory. It's not because of their region on pre or postsynaptic. It's just they do different things within
Yes.
the same type of neuron,
Yes.
but in a different region. Okay.
Okay, so to answer your questions both, talking about the GABA inhibitory receptor and the excitatory. So what's your question here?
Basically, like, can you explain how depolarization makes excitation?
Okay, so how depolarization leads to the excitation? Okay, so the first step in the signal transduction, remember? So this shows the action potential, basically the difference in charge across the membrane, inside and outside. Which one is negative? Which side is positive? Which side is negative on the membrane? Outside positive, inside negative. So the difference is right here. In the resting potential, we have what? Minus 90. Okay. So if you reduce the difference from minus 90 to minus 50, there's a threshold here. If you reduce the difference up to minus 50, then automatically the process starts. Okay. So you stimulate the process and the action potential starts. You get depolarization. So now you have the opposite. Okay, so you have outside negative, inside positive. And then this stage is repolarization. So you repolarize again. You will go back to this stage, which is the same level at here. And then you have hyperpolarization. Now the difference is even more. Okay, so in order for you to prevent the first stage here, if you make the potential below minus 90, it will make it more difficult for depolarization to occur. How do you increase the difference? If you have positive outside, negative inside, how do you make the difference even more? Chlorine inside, you can add, exactly, you can let chlorine get inside. So now you have chlorine is negatively charged. So you have more negative charges inside, so difference increases. This is exactly what GABA does. So GABA binds to the GABA receptor. The receptor is a channel. It lets the chlorine gets inside. And now instead of minus 90, we have like minus 200, for example. So it would be very hard to bring it to the minus 50 to stimulate the receptor. So we get inhibition at the neuron at the receptor. No, no. GABA is only specialized in chlorine. That's it. Okay? GABA is specialized in chlorine, which is negatively charged. So when we stimulate the GABA receptor, and if you remember the GABA channel, it's actually not a receptor. If you remember the GABA channel, it has different binding sites to the GABA, to the benzodiazepine, to the barbiturates. Okay, all these modulators, they increase the activity of the GABA ion channel. So now it lets ion inside negatively charged, so the difference increases. Okay. So that's how it gets hyperpolarized, it gets inhibited. This answers your question? Yes, because well, they both work on the chlorine, but barbiturates has the ability to increase the activity of the chlorine much, much more than benzodiazepine. So benzodiazepine has, let's say, this efficacy. Barbiturates have higher efficacy, higher effect. So that effect could be, from, anti-anxiety to sedation to hypnosis to, going into a coma and respiratory depression and even shutting the whole brain off and death. Okay, they have all these higher levels depending on the dose. So that's why it's been actually, avoided. Okay.
Can cause GABA receptor to open up without the presence of GABA. Is not a reason why
True. Barbiturates can work by itself. It does not need the presence of GABA. Benzodiazepines requires the presence of GABA. Maria, what was the question again? This one here? For what? GABA? So the GABA channel itself, the GABA receptor, the ion channel. Okay. I don't have the note here. So this is in line what we were talking. The channel itself, the ion channel, has allosteric sites for the benzodiazepines that are different from the barbiturates. Okay. Yes. Barbiturates also binds allosterically to GABA, but a different allosteric site. They bind, no. Where do the non-benzodiazepine bind to? Allosterically, where? Not on the GABA site. So only the GABA molecule binds to the GABA active site. So we have active site for the GABA, we have allosteric site for the benzodiazepine, we have allosteric site for the barbiturates. What about the non-benzodiazepines, the Z drugs, the Ambien and so on? Exactly, thank you. They bind the same allosteric site for the benzodiazepine. So why did you call them non-benzodiazepine? Because there's no benzodiazepine nucleus in their structure. So they have different structure, but they still bind to the same allosteric binding site of the benzodiazepine. Okay, thank you. Okay, I know you had many questions, but I really have to go. So I'm trying to get the most important ones. So if you really need the question to be answered here, raise your hand. Okay, what else? Who else? I have one. I just try to count. If your question is something you can send by email, please do. If something you need it now, raise your hand so I can see you. I have one already here. Okay, go ahead. Oh, so do you know, do we already know that the reuptake inhibitor, right? We didn't know. So if it's a reuptake inhibitor, we know the effect. If it's a GABA reuptake inhibitor, is it going to cause a stimulation or inhibition? Okay. If it's something that inhibits the degradation of the GABA itself, like the transaminase, and it is an enzyme, just like the concept of the MO and the COMT enzymes that break down the neurotransmitter, we have GABA transaminase that breaks down the GABA. If we block this enzyme, what happens? More GABA. And on the other hand, on the stimulatory, we have glutamate that binds to these receptors. So if we block these receptors, what happens? Less stimulation. Finally, if we have the calcium channel, forget the agonist, negative allosteric modulators at the calcium channel, then again, calcium will inhibit, because calcium is the one that causes the effect. And then if we block this, you have inhibitory. Now, imagine if you have, what would you need to have a stimulatory effect, okay? Well, in this case, so all these mechanisms are inhibitories because, of course, we're trying to look at mechanism of actions of anticonvulsants, okay? But if you look for an excitatory, then you could think of different ways. Okay. Of course, there's something that prevents the GABA release or storage, so you get that. And you both have the same question? Mhm. Mhm. Okay, that's a good point. Guys, we have two different synapses here, okay? This is one synapses. So in this part, it's presynaptic, postsynaptic. Herein, that's a different synapses. So this would be the presynaptic, this would be the postsynaptic, okay? So this is just, a way to represent, how neurons interact with each other. If this is the synapse, the signals go in this way, this is pre, this is post. At the same time, for this synaptic cleft, this would be the pre, this is the post. GABA? Yeah, you could. GABA receptor at this neuron, you can, yes. So the receptor, the neuron has more than one site. You have to look at the overall effect of inhibition, stimulation, and the overall effect will be whatever is the most, the summation. And your question? Benzodiazepines are positive allosteric modulators. Why? Because they stimulate the GABA ion channel. When the GABA ion channel is stimulated, you get more of the chlorine inside, the difference in the charge increase, hyperpolarization, which causes inhibition of the neuron. Okay? We do. I think one of them is called carbolin or something, but don't worry about it. Okay? And we also have neutralizer, which one it is? Thank you. Which is used as antidote, right? Okay, any urgent questions? Anything that you cannot ask by email? No? Okay, well, sleep well, okay, because again, when you're able to recall what you studied, when you have enough sleep, it's more important, okay? Sleep well and, be awake, fresh. It's gonna be, you'll do great. I'm sure all of you will do good, okay? So don't be stressed out. All right, and I'll see you on Monday, tomorrow. John.
I was just trying to see what figure where you got it. You just showed it.